hopefully fairly brief podcast about the nature of sound waves, part of topic 4 waves and subtopic 4.2 travelling waves. Okay, so the areas we're going to be focusing on today are the nature of sound waves under the understandings and the skills, solving problems involving wave speed, frequency and wavelength, with an example we'll come up with. And it does mention specifically investigating the speed of sound experimentally. So we'll mention that, and we'll be using the equation we've been using for a short while now, which is c, wave speed equals frequency multiplied by wavelength. So just like we've previously looked at what is sound and what is the nature of sound, previously we looked at what is light, we're going to look at what is sound. It's something very different. Sound waves are pressure waves. They are waves of compression. And so when this speaker is operating, sitting in a room filled with air, the speaker surface vibrates, and as it vibrates, it pushes the air particles into each other. These air particles move along and push into their neighbours, and so on and so on. And every time you get a vibration, every time you get an expansion, then a wave, a compression wave, a pressure wave of air molecules is pushed out. So to summarise, sound needs a medium. Unlike light, where you have a disturbance in an electromagnetic field which permeates the universe, sound has to travel through a physical substance. Sound is a mechanical wave. We've mentioned vibrating surfaces, so that's loudspeakers, musical instruments, the vocal cords which allow you to speak. Rapid expansion, that's how explosions make loud noises. That's how lightning, a bolt of lightning has very high temperature and it superheats the air that it's travelling through, which leads to a very rapid expansion, which leads to a compression wave. And the compression wave then propagates throughout the medium. Compression waves, also known as pressure waves, and these areas that you can see sort of between, so you have a compression wave travelling out and the areas between where the medium is less dense than normal, so here it's greater density than normal, here it's less dense than normal, those are known as rarefactions. This diagram shows, this animation shows a similar thing, but instead of sort of spreading out in 2 dimensions, it's sort of going along a pipe. And this shows that all sound waves, all pressure waves, are longitudinal waves. You might remember the definition of a longitudinal wave is one in which the direction of the oscillation is parallel to, or is in the same direction as the movement of the wave. Like all waves, sound waves carry energy, and this diagram neatly shows how the sound waves travel throughout the material from left to right. But although the waves are travelling through space, the actual particles aren't. Well, they are, but only just by a small degree. So every one of these red dots, but this applies to every dot, look for the black dots as well, is just actually vibrating through a certain bit of space. It seems weird because you kind of imagine that these particles are moving all the way. They're not. The wave is passing from left to right. The particles are not. The particles are all vibrating, and they're all vibrating, by the way, with the same amplitude. It doesn't matter where we go along here, everyone is vibrating with the same amplitude, is being displaced to and from its neutral or equilibrium position. Since sound travels through a medium, it has a velocity. The speed of sound depends on the nature of the medium. It depends on what it is. And the other thing it commonly depends on is temperature. So this graph neatly shows, I like it, it shows how the speed up through the atmosphere, the pressure and density decrease, like that. And you may have heard that the speed of sound depends on pressure and density. It doesn't. It depends very much on temperature. So you can see how the temperature varies up and down as you go through different layers of the atmosphere, and the speed of sound matches that. It does depend on the type of gas as well. So one of the numbers, there are a few numbers in physics, which is a good one to remember. And around 330, 343 meters per second for air at 20 degrees C. It's actually 330 at 0 degrees C is a good one to remember. But it can vary. So helium, it goes a lot faster, 965 meters per second. That's one of the reasons, by the way, that if you fill your mouth and lungs with helium, which you shouldn't do for long because you can't breathe helium, it's not poisonous, but you need oxygen. But if you do that, then your voice goes all funny. Your voice goes all funny because of the speed of sound is so different. But it is slowest in gases because the particles in gas are further apart and they're not closely linked. They don't have bonds between them. Whereas in liquids, it's faster, and in solids, it's much faster again. How do you measure the speed of sound? Well, the speed of sound in air, or the speed of sound in free air, in other words, if you're not trapping it inside a tube, can be measured by a couple of different methods. Here are two of them. One very low-tech one using a stopwatch and some kind of noise-making device. Just put yourself a long distance away from a flat surface that can create an echo. This diagram on the left is certainly not to scale. And make a noise, wait for the echo, measure the distance, and the sound wave has travelled to the surface and back. So in this case, it's travelled 960 meters, and use the timer to calculate the velocity. Now we've said previously it travels about 330 meters per second, so you should hearing an echo just under 3 seconds. Using a bit more technology, you create a noise, sound waves travel out, and you have two microphones spaced 1 meter distance away from the sound source, and using a fast timer, you can measure the difference in times and therefore again calculate the velocity. Just a couple of other applications to finish with before we look at a question. Sound waves is sound waves, but they're not the only type of compression waves. Another example that you might come across is seismic waves, as are created by earthquakes. There are 4 main types of seismic waves. You can forget these two, which are the Rayleigh waves and the Love waves, not named after Mr. Love, Dr. Love, who came up with them. But the other 2 types are P waves, which stand for pressure waves, and they are the pressure waves. S, which stands for shear, are transverse waves. P waves are longitudinal. And these have an application because these 2 waves get transmitted on the surface, but the P waves and the S waves can travel through the Earth, and by mapping where the waves are detected and by knowing the characteristics of how these waves travel, something due to refraction, which we'll be looking at shortly, you are able to map the interior surface of the Earth. And similar experiments have been done on other planets now, and the Moon. Further applications in the field of astrophysics are pressure waves within stars, within our own sun. Helioseismology is an ongoing study for 50 years now. And even pressure waves inside the plasmas, the materials that made up the very early universe, the instance of the Big Bang. These discrepancies in temperature of the microwave background radiation are caused effectively by sound waves, by pressure waves inside the very early universe, which is a fascinating topic we might look at later. Thought we'd just have a look at one question to do with sound. Again, there aren't very many questions to do with sound, and they're not always very easy to answer because these description ones, sometimes the mark scheme can be quite precise. So I found this one from 2015. It's part of a larger question about simple harmonic motion, but it tells you that you have a loudspeaker vibrating with a frequency of 1.25 kilohertz. So that's 1250 hertz, hopefully you recognize. It asks you to calculate the wavelength. Well, that's our old friend C equals F lambda. You know the speed, you know the frequency, so you can calculate the wavelength. Just 1 mark for that. Bing. It works out to about 0.264 meters, because this is 330 divided by 1250. Describe the characteristics of sound waves in air. 3 marks. You're looking for 3 different things here. There are a few things you could answer here, but what the mark scheme in particular is looking for is firstly the fact that they're longitudinal waves, which I think is a pretty good answer. That they travel through the air, travels with constant speed. I'm not so sure about that. I think that's kind of obvious. It says it's a sound wave in air, so it travels through the air. Again, that's what the mark scheme says, so make sure you know it in case it comes up again. And it's made from a series of compressions and rarefactions, which I think is regions of high and low pressure. That's not exactly the same as longitudinal waves because, for example, you can make longitudinal waves that aren't exactly high and low pressure areas. But so yeah, this first one and this third one I have no problems with. This second one, though, I thought was not an easy mark to get. Okay, so we've covered the nature of sound waves, we've had another go at solving problems, and we've briefly mentioned the investigation of the speed of sound experimentally, although of course that's a skill that it would be good to develop in a practical sense. Thank you very much.